Okay, welcome back to lecture 23.3, where now we can really ask what happens at a phase transition. Okay, so what we said last time was that the system always has to minimize the G, right? If temperature and pressure are important variables, we must minimize or lower, say minimize G. Okay, so if we had, where I'm now going to define a little g, which is simply here my G per unit mass. Okay, my intrinsic form of the Gibbs free energy. And if I imagined two situations, one where I had, for example, water, and one where I had ice, what I had was the system needs to minimize G, and so I have to follow whichever has the minimum G. And at this point then is my phase transition. Here it's called Tm. For water, this would be at 0 degrees, right? As we all know, if our pressure is at 1 atmosphere. Remember, when I tell you the phase transition temperature, I don't tell you the temperature and the pressure. I mean the temperature and the volume. I tell you the temperature and the pressure, right? Going to show the temperature and pressure really are the important variables. Okay. Okay, so imagine looking at just that minimum. So let's erase our higher energies. And let's look at what happens when we go now from water was minimized to ice. Okay. What happens at this point? What happens to G versus T? You should be able to know that you could see that we had a change in the slope, right? So that means at a phase transition temperature, or I'm just going to call it TC, a critical temperature, we're going to have a discontinuity in partial G, partial T. Again, this was at some constant pressure. Okay, so this is really cool. We know now that at a phase transition, what happens is we have the G's meet, and we had two different curves, so now we have a discontinuity in partial G, partial T. Okay, so let's look back at our big table of all of our free energies, right? Remember G was U, so I'm going to write it like G of T and P is U plus PV minus TS. Or T minus TS plus PV is what I have in my notes. All right, since G, the important variables are natural variables T and P, I can write the differential dG as, let's see, it should be minus S dt plus V, nope, should be minus again. Minus V dP. Let me just make sure that's correct. Nope, it's plus. Right, because it's minus when it's minus P dV. Okay, good. So we can realize that that would be the same as saying it should be partial G, partial T at constant at constant P, plus partial G, partial P, constant T, dP. So S is minus partial G, partial T at constant P, and V is partial G, partial P at constant T. Perfect. So we just said that we have a discontinuity in partial G, partial T at constant P. So a discontinuity in G, right? We actually have a jump. We have a jump. Have a jump in S. All right, so let's look here. So here you can see my slopes are negative, right? So my entropy is going to jump positive. Okay, so let's plot that. So if I have G, let's write it as big G over M for now. It's a function of T. TC, some phase transition. If I were to plot S, let's make it per unit mass too, just for the heck of it. At that same TC, how does this look? All right, so this is the slope. You can see that the slope is, I drew it so that it's getting flatter. And so it's increasing, it jumps, and it increases some more. Okay, so this was, for example, the solid and the liquid. Solid, liquid. Right, there's a kink here. And so there's a discontinuity, a jump in this, right? In the entropy. So you can see some of these things have to make sense. So if delta S is positive as T increases, that makes sense, right? We have to have that the entropy is going to increase as we increase in temperature or decrease as we decrease in temperature. So this slope must approach 0 as T goes to 0, right? Because that slope is just the entropy, and so this must go to 0 to obey the third law, right? So you can see that the third law is obeyed there. And really, I like to think about this really in terms of the third law. You can imagine that if I were, say, some system, and I'm starting to cool down, right? And I were to imagine continuing on that curve, I would have ended up with too much entropy. Right? And that's not allowed. And so the system must do two things. One, it must drop onto a lower entropy curve, and the system can remove entropy as T goes to 0 by having a phase transition. So that's really key. And we've seen that before, right? We've seen that when we had the latent heat, right? So there's a latent heat here. So the change in entropy, we called it at that point, was Q. What was the notation we used? Q. What did we call it? In my notes, I have QR. I don't know. I don't think that's actually what we called it. Let's call it delta Q over T at Tc, right? And that delta Q was the mass times the latent heat. And so we had delta S was mL over Tc. If I actually had written this in terms of little s, right? So if little s was, let me see if I can try to make that clear. Little s is big S over m. That would just be L over Tc. Excellent. So we get a discontinuity. So a kink in G versus temperature gives us a jump in our entropy. And we already know what that entropy is. It's our latent heat. Okay, so if we were to look on a larger scale, right? This is S over M versus T. For water, you would have multiple phase transitions, right? Let me make that bigger. All right, so this would be a solid, this would be the liquid, and this would be the gas or vapor. This would be T freezing, this would be called T melting, and so this would be the latent heat of freezing over Tf. And this quantity would be the latent heat of vaporization over T melting. Or sorry, not T melting. This called boiling. Excellent. So one note, we call this a first, these are called first order phase transitions. And originally, these were called that in what's called the Ehrenfest notation. I think I've spelled that wrong. Because they have a discontinuity in the first derivative of the free energy. Nowadays, they're called first order phase transitions because they have a latent heat. But you can see those are actually the same thing, right? There's only some, they've changed this definition because there's some really exotic kinds of phase transitions. For most of our phase transitions that we'd ever worry about, this is sufficient to think about them as discontinuities in the first derivative of the free energy. Okay, in the next section, we're gonna see another one of these discontinuities.